type of a carbonyl compound that we're going to talk about is whenever you have a carbonyl compound that is unsaturated. And I'll see if I can go ahead and just find a generic example of what I'm talking about. It would be something like this. So in this molecule here, it's unsaturated. There's a pi bond with a carbonyl atom attached to it. And I'm just going to go ahead and explain the nomenclature. So the carbon that's always right next to the carbonyl carbon, that is always designated, I'm just going to use English lettering, A for alpha. And then the one right next to it is, I'm just going to again use English, B for beta, but you should use Greek symbols for these. And some notes that I think need to be made about it is that this is a conjugated system. It's only separated by one pi bond, and there you're going to have p orbital overlapping. So along with this, we have certain reactive sites that I need to discuss. One of the reactive sites in our molecule, and I'll go ahead and switch colors here, is the actual carbonyl compound. That's nothing new. And then the other reactive site would be the alkene, the carbon-carbon bond that's attached to it. So if you have a nucleophile reacting with the carbonyl carbon, we call this the alpha attack, because it's attacking the alpha carbon. And what you get out of this is known as the 1,2 addition, as if you haven't seen that before, addition product. And so I'm going to go ahead and just draw a generalized overview of what I'm talking about. So again, I'm going to go ahead and draw my conjugated carbonyl system here. And it's called an alpha beta unsaturated carbonyl carbon there. And I just react that with any type of a compound that's going to give me a nucleophile, any of the ones that we just listed earlier today. So I react that with a nucleophile, and I run that reaction in water. So my outcome is this. I have a hydroxide group, where there once was that from the deprotonation reaction, and the nucleophile attacks there. If you don't know how these reactions work at this point, I'm very scared for you. Nucleophile attacks, carbonyl moves up there, and then deprotonation takes place. This is designated this as a 1,2 because this is the first addition site, and this is the second addition site, if you would like to think of it this way. Now, if we have, say, a nucleophile attacking here, so I'm just going to go ahead and just draw that out. Or actually, let me change up a bit. I have my nucleophile that decides to attack this carbon of the carbonyl compound system. This is sometimes called a beta attack because I'm attacking the beta carbon there. For this would be the 1,4, or you can even call it the conjugated addition. So let's just draw a generic mechanism. I'm going to go ahead and just circle this is the 1,2 over here, the 1,2 addition mechanism. And I'm going to go ahead and draw out the 1,4. So I have a generic substance here. There's a carbonyl there. I don't really care about that. At this point, it's going to react with this here. I go ahead and just run this reaction, keeping it broad, with a nucleophile in water. And my outcome, this may take a little bit more explaining than the other one did. Gives us a carbonyl compound there. There's a carbon there. There's a carbon there. There. And I'll switch colors to show what I added that was new. Added a hydrogen there. And then I added a nucleophile there. So let's draw the mechanism for each and every one of these. So let's draw the mechanism for the 1,2 addition reactions. We start off with our generic unsaturated carbonyl system there. And I have a nucleophile. Any kind will do. It doesn't really matter. We're not picky about this. I'm going to keep it abstract just to show you. It does what it does. It reacts with that there. In doing so, concertedly moving some electrons to the tip of that oxygen. So this is what I get with a nucleophile there attached, and then some lone pairs on that oxygen. And floating around in my mixture, obviously I run this in the universal solvent of water. And oxygen, this is nothing new. You've known how these reactions work since chapter 10, but I'll just draw it again. And what I get out of this is Okay, so that's my product. Nucleophile attaching here, and then a hydroxyl group there. That's nothing really new, nothing that's difficult to understand. So 1,4 mechanism, though, or the conjugated addition, if you think about it, this is going to be a little bit more unexpected. And any nucleophile will do. And rather than reacting with the carbonyl carbon, it's going to react with one of the carbons of the alkene system. And in doing so, moves an electron on top of the carbon. Now, I'm really wondering how efficient this is, because you are forming a carbanion in this process, but it doesn't. I wish my book would give more details on the efficiency of these reactions, but it never does. But nevertheless, that is what you get. Okay, so there's the carbanion that we talked about. There's the nucleophile that's attached to it. I should make note that this carbanion, hopefully you understand that carbanions have negative charges, and it doesn't want to stay in that conformation for very long, and it's not going to. So the carbanion is going to move down here inward. Now, carbon can't break its octet rule, and so what it does is it just pushes some electrons up on the tip of the oxygen. So keep in mind that we are running this reaction in water. I'm just going to go ahead and elaborate on that, and what happens is the same thing that happens with any time you have an alkoxide anion floating around in water. It's going to steal a proton from that. So here's where things get kind of interesting. It undergoes a unique type of reaction. I'm just going to go ahead and write it out here. We talked about it, I think, when we were talking about alkyne reactions, but it's called a tautomerization reaction. See if I can get that to fit. And basically, in a tautomerization reaction, you're going in equilibrium with an enol converting itself to a ketone, and then that ketone will be converting back to an enol, but it's not favor. Obviously, it's going to favor the ketone more so than that. I'm going to draw the mechanism behind that, but that's what this type of reaction is called. I just went ahead and redrew that, whatever this type of molecule is. So this is where the tautomerization process starts to happen. So as we had talked about in chapter 10, I think with alkynes doing this, it was usually an acid type compound. I think the solution only runs it in water, which I think is very odd. But a lot of the times whenever our book says that we're running a reaction in water, they just use that as a proton source, and you can use it as an acid. You can use acid type compounds. But either way, just like with any other alkene reaction, it's attracted to the partial positive end of the hydroxyl group, or of the hydrogen in the water molecule, reacting to form a hydroxyl group. And then okay, so that's my nucleophile from my first reaction. That's my hydrogen from my first proton transfer reaction. And this right here is the hydrogen from when it's still there. It obviously could happen on either side depending on where the carbonyl carbon, depending on where the double bond is. And we have a positive formal charge here. Now, it's going to be more stable in that state for multiple reasons, but remember that there's lone pairs on that oxygen. And this is where it gets into it, that those lone pairs of the oxygen can contribute. Even though it doesn't want to do this, it's going to do this to fulfill the octet rule, which is going to give us a major conformer for our resonance structure. So when we move that lone pair down, we end up forming a now satisfied octet rule, but the positive formal charge has to go somewhere. It goes back to the being on the oxygen, and that is just really ugly, right? It's very uncomfortable. But floating around in my solution, I have either water molecules from, if I had used this as H3O, or hydroxide molecules from if I had used water. And what this gives me is a proton transfer reaction that's going to remove that extra hydrogen there. So I'm just going to go ahead and draw it like this, that it's going to go there. I didn't draw a bond there, but just imagine if you had lone pairs going back on the oxygen. And at the end of the day, what this gives us is a ketone, which is what's favored at equilibrium of tautomerization reactions. So let me draw that one out. So at the end of the day, I just went ahead and circled our product in magenta. We end up getting the ketone. I don't think I finished drawing out all the other boring things there. But we have a hydrogen we've added here, and we have the nucleophile that we've added here. And that is every single step that we need to have. The most confusing step being the tautomerization step. But just keep that in mind when you're going through these. I think I mentioned this, was that 1,2, if I want to get the 1,2 alpha beta unsaturated carbonyl product, I tend to use some type of organolithium reagents carbon with a lithium, or I can use a Grignard reagent. And I don't quite understand this, I guess mechanistically speaking. Obviously these are stronger than the latter of which I would use for 1,4. And I'm going to stop using, I guess, abstract examples of this. I use organocupric reagents. If I want to obtain the 1,4, obviously we know that this is much weaker than the other two, but that doesn't fully explain the nature of the mechanisms that we just saw. You figured the stronger one would be better at attacking the alkene, but perhaps there's something greater at work there than what we had previously been speaking of. Anyways, so that's that.